So you've already been doing some algebra proofs and setting that up in a two-column type of format, but basically it was like solving an equation, and then for each step of solving you're writing the property that supported that step. So now we're going to switch our focus to starting geometric proofs. And when we're starting our geometric proofs, we have to think about our definitions that we already know, because right now they are going to lay the foundation for our reasons in our geometric proof. So thinking along those lines, I'm going to set you up with what we call mini-proofs. And mini-proofs is me giving you a statement, and then that's a given statement, and you then telling me what you can conclude from that. Right? So it's very much like our deductive reasoning skills that we learned in the beginning of the chapter. So here we are told that B is the midpoint of AC. And this should actually have a little segment on top. So let me fix that. B is the midpoint of segment AC. Now, using our definition of a midpoint, what can we conclude? Well, this is where it becomes so important for you to know your definitions. The definition of a midpoint is that it is a point that divides a segment into two congruent segments. So if B is the midpoint of AC, if you need a little kind of picture to see what that would look like, here's your segment AC, B is the midpoint, and then we put our tick marks there, right? Therefore, what we can conclude is that segment AB is congruent to segment BC. So if this was thinking in terms of a proof, if step one, we were given this, so there's my statement, here's my reason is that it's given. Remember, we always start first, reason is given. Two, there's our statement, that's what we can conclude from the given, and the reason would be definition of midpoint. Okay, that's your first geometric proof. So here's our next example. If we are told that ray RT is bisecting angle QRS, what can we conclude? So if we think about this again in a two-column proof format, if this is my first statement and our reason is given, what do we know next? If you need to, you could draw a little sketch of what's happening. So here is RT and it's bisecting angle QRS. So then what do we know? Well, by the definition of an angle bisector, right, we know that an angle bisector divides an angle into two congruent angles. So then we know that angle QRT is congruent to angle TRS. And our reason here would be definition of angle bisector. So next example, E is between D and F. Okay, so remember what it means to be between, that E is lying on that same line anywhere in between D and F. So if we bring in a sketch of what this would look like, there you go. Okay, now let's set up our little mini proof here. So if this is my given, okay, what can we conclude next? Well, think back to when we learned between, which was in the beginning of chapter 1. The only thing that we could deduce here is that if E is between D and F, that would be our segment addition postulate. So that we could say that DE plus EF equals DF. Now notice my notation. I'm talking about the lengths of the segments, right? The lengths of the segments, the notation does not have a segment bar on top. It's just strictly those two points. So it's DE, the length from D to E, plus the length of E to F is equal to the length of DF. And our reason here is just going to be the segment addition postulate. Remember, a postulate is a statement that we accept as true without proof in mathematics, okay? Postulates and definitions are very similar because we know that they are statements, they're facts that we don't have to go through the proof of. Alright, so now this example is a little bit different here because it's not necessarily a definition that we're going to be using to support our statement. So if we are given, so again, let me set this up in a proof type of format so you get used to that, okay? If we're given that the measure of angle 1 is equal to 58 degrees and the measure of angle 1 is equal to the measure of angle 2, what can we conclude? This is actually an algebraic reason, a property that we've used before. When you know the value of something, of a figure here, this is the angle measure, the degree measure of angle 1, right? And we know that the measure of angle 1 and angle 2 are the same. They are equal. So we want to use a property called substitution. We are going to take 58 degrees and substitute it in there for your angle 1. That measure of angle 1. So what can we conclude? We conclude that the measure of angle 2 is also 58 degrees. And this is a very common reason that we use, which is substitution. Okay, that's the substitution property, which says that you can substitute a value in for its equal. So here's our last example of a mini proof. I drew the segment right underneath it so you can see what's happening. We are told that AB is equal to CB. So again, notice the notation. There's an equal sign because we're talking about the lengths. Over the segment, over the actual letters like AB and CB, there are no segments, right? There's no segment notation. So that means that we're talking about the lengths. The lengths are equal here. Now, if you know that the length of AB is equal to the length of CB, it's a very common process that we do in proof. Okay, so here's 1, let's say this is given. Okay, so if the lengths are equal, that means that the segments themselves are congruent. So what we can say is that now segment AB is congruent to segment CB. Now our reason here might be a little bit tricky. If we know that the segment lengths are equal, we then know that the actual segments themselves are congruent. That is by the definition of equal segments. Okay? Or we can say the definition of equal measures. Okay? Those are interchangeable, really, because we're going to be using this with angles as well as segments. Now this one's interesting, this proof, because we could actually go 3 steps. If we now know that these segments are congruent, I can mark that on my sketch, right? And what does that remind you of, those markings? It should remind you of a midpoint, right? So you see that B is that common point between those congruent segments. Therefore, we know that B is the midpoint of segment AC. And how do we know that? That's by the definition of a midpoint again. How does that work? Well, we know that if 2 segments are congruent and they share that point then becomes the midpoint, because that point divides a segment to 2 congruent segments. This is a biconditional, right? A point is a midpoint if and only if it divides a segment to 2 congruent segments. That's what's happening here, so that's how we get our third statement. Okay? I think we're going to be ready to do some real proofs now, more than just 2 to 3 steps.